Okay, welcome. So this is the first lecture for the spring semester of Introduction to Partial Differential Equations. And so what we're going to do in this lecture is just go over some introductory material. For example, talk about what partial differential equations are, look at some simple examples, and talk about some common terminology and notation that we use when talking about these types of mathematical objects. And then at the end of the lecture, we'll also spend a little bit of time reviewing some important tools from multivariable calculus, which some people may not have used a lot or may not be familiar with, but which we will use a lot throughout the semester. And so I wanted to devote some time towards a little bit of review. Uh, and then in the next lecture, we'll actually start looking at specific equations and talking about how to solve them, right? So today we're not going to see how to solve any particular partial differential equation, but we're going to introduce some tools that we'll be using very frequently throughout the rest of the spring. Uh, and so just to begin, well, what is a partial differential equation? Well, these are commonly people will abbreviate partial differential equation as PDE. And so PDEs are just differential equations, uh, as you can tell. Uh, just from their name, but what distinguishes partial differential equations from the differential equations you've encountered previously, the main difference is just that they involve more than one variable, right? So they involve, say, two or more independent variables. Right, so for example, maybe you have some function u, which is a function of maybe two variables, say x, y, which you can think of as being points in the plane. So these are like the position or the spatial variables, but maybe it's also a variable, a function of time too, right? So as time evolves, the function changes in some way, which could be different at each point, right? And so partial differential equations will involve functions of several variables and also involve different partial derivatives with respect uh, to the different variables that the function is defined with respect to. So for example, maybe if you take the derivative with respect to time of u, maybe this is equal to the first derivative with respect to x of u plus twice times the first derivative with respect to y of u. Right? Right, so this is a simple example of a partial differential equation because it's some equation involving the function uh, and several different derivatives with respect to different variables. Right? Uh, and so, I mean, usually it's common notationally for x and y, or maybe z if you're in one higher dimension, to refer to like spatial variables, right? If you're thinking about the physical perspective. And then, of course, t is usually used to denote the time variable, right? So as t changes, you're thinking of some physical system, which the equation describes evolving over time. Uh, Okay, and so let's look at some simple examples, which again we're not going to talk about how to solve today, but in the next several weeks we'll uh, discuss how to find solutions to all of these examples that or most of the examples I'm going to mention now. Uh, so the first is, well, this is a pretty common example to begin with. So let's imagine a vibrating string. For example, you have a guitar and you pluck the guitar string, and then the guitar string vibrates over time until eventually it stops. So it turns out that this phenomenon can be described pretty accurately by a partial differential equation that's by a partial differential equation, which is one of sort of the core equations that we'll be looking at later on. And so how do you set this up? Well, let's imagine that we have some particular vibrating string. Let me try to graph it here. Like, let's say this is the x-axis. And so maybe the string looks something like this. Maybe some kind of something that looks a little bit like a sine wave. And so what I'm going to do is I'm going to define a function u. It's going to be a function of x, where x is the point on the x-axis, and also a function of t. And this function is going to be the displacement from the x-axis at time t and point x. Right, so for example, maybe this is my point x naught, and say we're at time t is equal to t naught. Well, then my function u measures the displacement from the axis, which is this vertical distance here, right? So this is over here, this is the value u of x naught t naught, which is on the y-axis, right? So maybe instead of calling this the y-axis, let me call it like the u-axis, because the value of u is like the height of the wave. Right. And so what we're going to imagine is that as time changes, this wave is oscillating up and down, right? So even if you fix a particular point at this particular time, maybe after a few seconds, the wave or the string has moved down here, or maybe it's going back and forth, right? So there's some physical system, which is this string which vibrates over time, and which we're describing with using this function of two variables, right? Okay, and so it turns out that under suitable hypotheses, this function u obeys what's called the wave equation, which we'll study in depth later. Right? And so the wave equation is the following. So if I take the second derivative with respect to t of u, where u is this displacement function, which is describing the vibrating string, this has to be equal to some constant c squared times the second derivative with respect to x of u. Of course, it's not at all obvious from the picture why this is the case, but we will, in a few lectures, we'll derive this equation using this picture, and you'll see why this equation works. And so it turns out that this c is just a constant, which is related to the speed of the wave. Right. Right, and so this will, for example, depend on some physical properties of the string, like how fast does the string vibrate. It depends on like the tension and the substance that it's made of, and things like this. Right, and so here we have a second derivative with respect to the time variable, and this is equal to some multiple of the second derivative with respect to the x or the spatial variable. Right, and so this is like a sort of a major example of a very important partial differential equation, which arises in a variety of contexts. In particular, this kind of simplified vibrating string model. Right, and so what's another example of a type of partial differential equation which we'll be studying pretty frequently throughout the semester? So now let's imagine that we're in, say, 2 dimensions, and let's suppose you have a heated plate. Right, so imagine this is some like plate of metal, right? Maybe plate's not the best description. Let's say a sheet of metal, right? And so now let's suppose that this is in 2 dimensions, and suppose we use x and y to describe points on the sheet of metal. And so let me define a function u of xy now, and also as a function of t. And I'm going to let this function denote the temperature of the sheet at point x comma y and time t. Right, so if you fix a particular time t, and then you go to a point x comma y, which is on the sheet, this function tells you the temperature, right? So we're imagining there's some heat source, and as time evolves, well, the heat is going to spread out through the plate in some way. And so the temperature at a particular point, say x comma y at time, say t equals 1, is not necessarily going to be the same as it is at time t equals 2. And also, as you move at different points in the sheet, maybe different points are have different temperatures based on like how the picture started or something like that, right? So you get some physical system, which is the evolution of the heat distribution throughout the sheet of metal, right? And so that's what this function describes. And so it turns out that this function obeys the heat equation, right? So U solves what's called the heat equation or the diffusion equation. which says that now it's instead of being second order in time like the wave equation, it's going to be first order in time. So if I look at the derivative with respect to t of u, this has to be some multiple, say k, or I guess the Greek letter kappa, times the first derivative, or sorry, the second derivative with respect to x, plus the second derivative with respect to y. Okay. Right. So again, on the left-hand side, this says the rate of change of u with respect to time is proportional to this combination of second derivative with respect to x plus the second derivative with respect to y. Right. And so unlike the wave equation, this is first order in time rather than second order. And we'll see that that actually makes a big difference for trying to solve it. That may not be obvious initially, but we'll see soon that even if you make a minor change, like passing from second order to first order, it dramatically changes, one, the methods that we can use to solve the equation, and two, like the properties that solutions to the equation will have. Right, and so I just want to mention that, right, so writing these difference quotients for the derivatives here with like d squared, dt squared, except d squared, dx squared, there's a common shorthand which kind of makes a lot of these partial differential equations a little bit easier to write out. And so this will also commonly be written now instead of, let's say, d squared dt squared. Instead, people, including the author of our textbook, will often write this as utt, which is shorthand for the second derivative with respect to u, is equal to c squared ux x, right? And so using this shorthand, if we move down to the second example, what this says is that now the first derivative with respect to t of u is some constant, say kappa times, well, now the second derivative with respect to x. So we put two x's plus second derivative with respect to y. Okay, so we put two y's there. Okay. So this is a common shorthand for partial differential equations, which we'll use frequently. Okay. And so now let's maybe just look at a few other quick examples, just to give you some other equations to think about, as examples of partial differential equations. So for example, maybe we introduce something a little more complicated, like maybe we have some function u, the function of x and y, and maybe the first derivative of u with respect to x plus u times the second derivative of u, or sorry, the first derivative of u with respect to y is equal to 0. So what does this mean if we unwind the shorthand? This means that the derivative with respect to x of u plus u times derivative of u with respect to y is equal to 0, right? And so this partial differential equation turns out describes shock wave phenomenon in a simplified model, but still, right? So this describes shock waves. Another example, let's say, let's say we look at the equation from before, which was the heat equation, where we had something like this. Right, so now let's say we add on a time variable as well. But instead of this number, this kind of arbitrary number kappa from up here, let's specify, and let's not actually use a real number, let's use the complex number I, where I is the complex number, which is the square root of -1. So this equation that I just wrote down is another important example of a partial differential equation, which is related to the Schrodinger equation from quantum mechanics, right? And so this describes the motion of a quantum particle in 2 dimensions in a simplified context, right? So this is actually like what's called the free Schrodinger equation, where there's no extra forces acting on the particle or something like this. Right. And so, well, throughout the whole semester, whenever we encounter a new partial differential equation, there's basically going to be two different ways that we're going to analyze the equation. And so let me just write those out. Right, and so the first thing is the simplest, which is kind of the most natural, which is kind of like the computational question. So this is just like finding solutions or finding particular solutions to a given PDE. For example, like the examples we saw earlier today. Right, and so again, as I just said, this is like a computational question. Like suppose you have some initial state in your physical system and you know that your system, which is given to you, and you know your system obeys, like for example, the heat equation or the wave equation. Can you write down this function u that we were talking about kind of abstractly above? Like what is this function actually equal to given certain initial conditions? Right, so this is a calculational or computational question. You just want to find something solving the equation. And so this is something we'll spend, of course, a lot of time talking about, in particular, starting the next lecture. But there's also an equally important related line of investigation, which is a little bit more abstract, which we're also going to be pursuing throughout the semester, which is to mathematically analyze properties of solutions in the abstract. Right, and so this is kind of going to be a kind of a more abstract approach, which is, let's say I have a solution to the wave equation in the abstract. Well, for example, how do these solutions behave? For example, do solutions decay over time or blow up or something like this? Right, so these are going to be kind of more general and abstract questions about kind of like an arbitrary solution to an equation. And so it turns out that, I mean, even though this may seem more abstract, understanding the kind of general properties in the abstract of a solution can actually, in some cases, help you solve the equation and find particular solutions. And conversely, if you understand like the solution formula, you can often derive mathematical properties of kind of abstract solutions from this formula. So these two things are kind of very deeply related to one another, and kind of one of the main themes of the semester is that when you're analyzing partial differential equations, you really have to understand both of these approaches, right? And so whenever we encounter a new equation, we'll be looking at these two things concurrently, right? Okay, and so of course, everyone here is hopefully familiar with at least studying ordinary differential equations. But what I want to do now is just talk about some kind of like the major differences in complexity between ordinary differential equations and partial differential equations, because it turns out that as soon as you add a second derivative operation with respect to a different variable, the theory completely changes, and partial differential equations are kind of like their own thing when compared with ordinary differential equations. And so I just want to do like kind of a simple example to illustrate why that's the case. Great, so let me just write, we're going to look at the difference in complexity. When compared with ordinary differential equations. Right, and so ordinary differential equations are usually abbreviated ODEs as opposed to PDEs, and that just means that there's only one variable that you're taking derivatives with respect to. Right, maybe you're taking a second or third derivative, but it's just with respect to one fixed variable, unlike the examples we just saw above. Right, and so for example, let's suppose we have a function which is a function of one variable x, and suppose it solves a simple equation, say this second derivative with respect to x is equal to 0, right? So let's suppose that f prime prime is equal to 0. And let's say we want to solve this ordinary differential equation. Well, everyone hopefully knows how to solve this. We just take antiderivatives, right? So if the second derivative of f is equal to 0, this means that the first derivative has to be equal to some constant a, which doesn't depend on the variable, right? And so, okay, well, now I know what the first derivative has to be equal to. I don't know what a is yet, but I have an idea of what the solution has to look like. And so, well, I want to find f, so let me take one more antiderivative, right? And so if I take an antiderivative of the left side, I just get my function f. And if I take an antiderivative of the right side, well, what's the antiderivative of a constant with respect to x? It's just that constant times x. But then there could have been another constant that popped up as well, right? So a and b are constants here, right, independent of x. And so this is kind of like the general form of my solution to this particular simple differential equation. Okay, and so how do we find out what a and b are? Well, in general, we don't know. You would need some kind of initial condition, right? So a and b are determined by initial conditions, right? So for example, let's suppose that we happen to know that when x is equal to 0, f is equal to 1, and also that when x is equal to 0, the first derivative is equal to 2, right? Well, we can use this information to solve now and actually find an explicit function which solves this equation with these given conditions, right? And in particular determines a and b, right? Because, well, we can plug in the fact that when x is equal to 0, this has to be equal to 1, right? So 1 is equal to f of 0. If I plug in x equals 0 here, this first term goes away, and so this is just equal to b. And so this, therefore, b has to equal 1. And moreover, well, if I look at f prime of x, this has to be equal to a. And if I know that f prime of 0, if I know that 2 is equal to f prime of 0, well, f prime of 0 has to equal a just from the above line, right? And so this tells me that a equals 2 and b equals 1, right? And so for these particular initial conditions, we have the solution to our ordinary differential equation just given by 2x plus 1, right? Okay, well, now what we're going to do is consider the same equation, second derivative with respect to x, but for a function of two variables. And we're going to see how things change, right? So now let's consider instead a function u, which is a function of two variables, x and y. And let's suppose, though, that we do, we have the same equation, right? So the second derivative with respect to x of u is equal to 0, or in shorthand, u xx is equal to 0. So how are we going to solve this equation? Well, let's just try to proceed as we did before. Right, and so what did we do here? Well, we just started taking antiderivatives, right? And so let's begin by taking antiderivative with respect to x. So here you have to be a little bit careful because this is a function of two different variables. So you have to really specify, well, which variable are we taking the antiderivative with respect to? So we're taking antiderivative with respect to x. Well, then on the left-hand side, taking antiderivative will reverse a differentiation operation. So we're just going to have d dx of u. Well, what do we have on the right-hand side? Well, if we just follow our model from before, this should just be some constant a, right? Right, so a is a constant, right? But that's not completely accurate because, well, what do we mean when we say it's a constant? We mean it doesn't depend on the variable that we're taking derivatives or integrals with respect to. But here there's another variable that's lurking in the background, which is this variable y, right? So it's perfectly plausible that maybe whatever this a is, it could depend on y, right? So a is constant with respect to x. But it could depend on y. And so this is kind of a big important point that may hint at the extra complexity of partial differential equations. Right, so this is actually a function of y, right? Rather than a constant, which we got in the previous example, we have a whole function, arbitrary function of y could be here, right? Any function of y you can think of, like e to the cosine y squared or something, right? Okay, so now let's continue then, and so let's take one more antiderivative. Right, and so on the left-hand side, of course, taking antiderivative with respect to x will reverse the derivative operation, so we end up with u of xy on the left-hand side, which is the function we're trying to find our solution. Okay, and so now what happens if we take the antiderivative on with respect to x on the right-hand side? Well, if we take antiderivative with respect to x of a function of y, well, this function of y is like a constant when viewed as a function of x. And so as before, we're going to end up with, say, x times a, whatever a is. But remember, a is an arbitrary function of y, right? But then there could have also been another term that depends on y that popped up, right? So plus, say, some b of y, where this could also depend on y, right? And so here in our final solution, it looks very similar to what we got in the ordinary differential equation case, but this whole factor, or the whole idea of just adding a second variable kind of complicated this and made these two things, forced these two a and b's to be functions of y. So not just arbitrary constants, they're arbitrary functions now of the other variable. Right, and so for example, let's suppose we saw before that in order to have something that's not like an abstract solution with kind of extra letters involved, you need to specify certain initial conditions, right? And so let's suppose that, or let's try to impose some initial conditions and solve. Right. Of course, if you didn't have any other information about your function, then you couldn't. This is kind of the end, right? You can't specify what a and b are because they could just be general functions, and so at this point we would be done. Right. So let's suppose that. Well, now say when x is equal to 0, as a function of y, u is equal to, well, we could really put any condition here. Let's say it's equal to e to the y, right? Well, what does this tell us? This says that, well, if I plug this into the equation up here, I'm going to plug in x equals 0. When I plug in x equals 0, the term involving a will vanish, right? So this says that e to the y is equal to u of 0 comma y. And now if I plug in x equals 0, the first term vanishes and I just get b of y. So this condition here forces b of y to be e to the y, the function e to the y. And now let's also, okay, so that tells us what, this one condition tells us what b is, but at this point we don't know what a is, so we would need another condition, right? And so as our second initial condition, let's suppose, say that the derivative of u with respect to x at 0 comma y is equal to y cubed, say, right? And so what do I mean here? This is like the derivative with respect to x of u evaluated at the point 0, y. Right? That's what I mean by this notation. Okay, and so how do we use this condition? Well, let's take the derivative with respect to x of this equation. So derivative with respect to x of the left-hand side is ux. And on the right-hand side, well, the b term vanishes because b doesn't depend on x. So when I differentiate this with respect to x, it'll be 0. And so I just have the derivative with respect to x of this term. And so this term is, as a function of x, it's linear. And so you just get a of y when you differentiate. Right, and so we have ux of xy is just equal to a of y. And so now if I use this condition, this tells me that y cubed has to equal ux of 0, y. which is equal to, using the above formula, a of y. And so this tells me that a of y has to equal y cubed. Great. And so with these conditions, with these initial conditions, our solution to the equation from above is given by x times e to the y plus y cubed, right? Because, oh, sorry, I got that backwards. It's given by x times y cubed plus e to the y. Right? Right. And so again, I mean, the method we used to solve this equation was very similar to what we used for the ordinary differential equation, where there was only one variable involved. But as soon as we added another variable, all the constants that we had before had to become kind of arbitrary functions. Right? And so this kind of indicates how, as soon as you start adding more variables, the complexity increases kind of dramatically, because, well, in particular, you can notice that our initial conditions here are no longer constants. Our initial conditions are kind of arbitrary functions. Right? And so let me separate this as kind of a key point. So for partial differential equations, your initial conditions will generally be functions, not constants. Right, so not necessarily constants. Right, and so if you want to think about like kind of the physical relevance of this, right, so the initial condition, which maybe is some function, maybe describes like the initial state of your system, right? So if we go back up here to the heat equation example, where we're looking at a heated sheet of metal, maybe your initial condition is given when T is equal to 0, and it describes like the initial heat distribution as a function of X and Y before time starts evolving. Right, and so this is one example where you would have like where it's physically reasonable to be like given a function which describes the heat distribution, and then let time evolve. That function that was given to you is your initial condition, which once you have, you can solve the equation, which we'll do in maybe like 3 weeks. Okay, and so this kind of necessity to allow general functions to be initial conditions for your equation does make things a lot harder. So this is one of the simple, no, I shouldn't say simple, but one of kind of like the first reasons you encounter that kind of indicates that partial differential equations are harder to study than ordinary differential equations. Okay, and so right, so there's a bunch of basic terminology and some extra notation I want to go through that we'll be using pretty frequently. But I think what I'll do is I'll begin the next lecture with that. Instead, to finish up today, I just want to talk about one topic for multivariable calculus, which is kind of an important tool which we'll be using pretty frequently, which some people may not have seen before, just because I don't know if these types of calculations are frequently covered in like your standard multivariable calculus class. And so what I want to end the lecture talking about today is a review, which may not be a review, and if it's not a review, it's perfectly okay. Although hopefully you understand kind of the tools that I'm using here. So what we're going to be talking about is derivatives of integrals in multivariable context. Okay. And so it may not be clear now, but it's going to become clear pretty soon that the typical solution formulas we'll have for the various partial differential equations we encounter are not always going to look very nice. And in fact, a lot of solution formulas that we're going to end up with are going to be kind of complicated formulas involving integrals of different functions. Right, so we're going to often encounter solution formulas of the form, say, u of xt, right? Maybe u solves the heat equation from before. So maybe this is an integral on some domain D. which I'll call dt, of some other function g, which also depends on x and t, and then a third variable of integration, right? And so this is some domain, and the domain could depend on time, right? So maybe your domain is changing as time changes. Right? And so unfortunately, it's kind of just the nature of the subject that a lot of our solution formulas will be of this type for some rather complicated looking function g, which depends in some way on the initial condition that's given to you and also on some other stuff, right? So for example, when we study the heat equation or the diffusion equation, we'll have a formula that looks exactly like this for specific functions. Right. And so while in kind of analyzing solutions to these equations, it's often important to understand how to take the derivative of these expressions, right? So it's often important to consider say the derivative with respect to t of u, where our solution u is given by a formula like this up here, right? So how do you take the derivative with respect to t of something like this, right? So this is the time derivative of this integral up here. Where we're taking the derivative of the whole expression, right? And so kind of one of the major complications is, well, this domain can depend on time, right? But this is my variable of that I'm taking the derivative with respect to, right? How do I differentiate with respect to time if my function has the time variable in like the bounds of integration, right? This kind of looks too complicated to deal with, right? And so what we're going to talk about now is in the last, like, say 10 or 15 minutes of the lecture is how to do that, right? We're going to review how to do this using some basic tools for multivariable calculus. And in particular, we're going to see that the multivariable chain rule is the main tool that allows you to do these types of calculations. Right. And so there are kind of two different cases to worry about. And so the first case is kind of the simpler case where the domain doesn't depend on time. Right. So your domain of integration does not depend on the variable you're differentiating with respect to. Right, so maybe like, for example, u of xt is given by an integral from, say, some number a to some number b, where these are just your bounds for integration and they don't depend on time, of some other function g, which could depend on time. Right, so we're still allowing the integrand, the function inside the integral, to depend on t, but now the domain doesn't depend on t, right? And so in this case, it's actually, it's not too hard to calculate these derivatives. So then derivative with respect to t of u is kind of exactly what you would expect it to be, right? So this is the derivative of this integral, which you can evaluate by taking the integral of the derivative, right? So this is integral from a to b of d dt of g, right? And okay, so what we've done here is basically switch the role of the differentiation operation and the integration operation, right? So the derivative of the integral is the integral of the derivative, as long as the integrand is a function of this variable t, right? Okay, and so this is not always valid for arbitrary functions, but it is valid as long as, for example, the derivative of g is continuous or something like this, right? And so we're not going to worry ourselves with these types of technicalities throughout the semester. So we're going to assume that for all functions that we're working with, this is a valid operation. There's a little bit of discussion about this in the appendix of the book. And if you've taken a class in real analysis, maybe you've talked in more depth or detail about when you can do this. But for us, we're just going to assume you can always do it. Okay. Okay, and so well, once you have this rule, you would actually know what the function g is, and you would presumably be able to calculate this derivative, and then you would be done. So for example, let's suppose u of xt is given by the integral from, say, 0 to 1 of sine of, let's say, xt plus y dy, right? So it's a function of x and t. This variable y is like your dummy variable of integration, right? But this integral here is like a function of x and t. Right? Okay, and so, well, how do I take the derivative of this? Well, if I apply the rule from above, this is just integral from 0 to 1 of derivative with respect to t of the integrand. Right. Well, hopefully everyone can now compute this derivative just using the multivariable chain rule, or just the regular chain rule, since it's just we're just taking derivative with respect to t here. So this is equal to now integral from 0 to 1. Well, derivative of sine is cosine. Right. But now I have to use the chain rule because I had this x times t. And so by the chain rule, there's an x that has to show up here. Right. And okay, so for this example, I mean, you could do like maybe some u substitution to evaluate this integral. Notice that the x doesn't depend on y, so you can just factor the x out, right? I'm not gonna do that calculation now. At this point, everyone can evaluate this. And your answer will be it's okay if your answer depends on x and t, because it has to, right? It's some function of x and t. You just have to make sure your answer doesn't depend on y when you calculate the integral, of course. Right, and so in this case, when again the domain doesn't depend on t, these types of calculations aren't that hard. So you may be wondering, like, why am I wasting time doing this? Of course, this is how you take the derivative of this type of function. Well, the sort of the interesting and more challenging case is, well, what happens if this domain did depend on time, right? And so this is something that maybe not everyone has seen before. Right, and so this is case 2. So in this case, the domain of integration can be allowed to depend on time. Right. Right, and so this is more complicated, and so we'll see that we have to use the multivariable chain rule to make sense of this. Right, and so what I'm going to do, I'm not going to do this in the abstract. Although if you look in the textbook in the appendix, I think these types of formulas are kind of proved in like kind of fancy abstract contexts. What I'm going to do is just look at this particular example from before, but just change the domain, and we'll talk about how to find the derivative of this particular function. Right, so let's suppose that u of xt is given by integral of the same function from before, say integral of sine of xt plus y dy, right? Integrating with respect to y, but it's some function of x and t. And let's say the domain of integration is from 0 not to 1 now, but to t squared, right? And so now the domain changes as time changes, right? And so the question is now, what is the derivative with respect to t of u, right? So what is the derivative with respect to t of this expression here? Right? And again, the big problem is that, well, I'm taking derivative with respect to t, but I have a t up here, right? So how do you make sense of this? Well, you may think back way back to your first calculus class where you hopefully did some calculations like this. But in those examples, maybe in the inside of the integral, you didn't also have another function of t, right? So you may think, oh, you just use the fundamental theorem of calculus, which will be relevant for how we do this. But the issue with using the fundamental theorem of calculus is that this was only valid if the integrand didn't depend on t, right? And so we have to be a little bit careful here, and you can't just say, oh, this is equal to sine of, right, what does fundamental theorem of calculus say? You plug in t squared for y and then multiply by the derivative of this. So this is not equal to, right, so this will not be like sine of xt plus t squared times 2t, which is maybe the most natural approach using the fundamental theorem of calculus. It's going to be a little bit more complicated. And again, it's because the integrand also depends on t here. Okay, and so how do we do this? Well, the idea is to, which is kind of maybe counterintuitive, but sort of the way to make this easier to understand is to actually introduce two more variables, which you would think like, how is introducing more variables going to make it easier? But it does. Uh, and so what we're going to do is, let me define a new function, which I'll call capital F of x, w, s. And this function, I'm going to replace the t squared and the t in my problem by two separate variables. So this is the integral from 0 to s of sine of, now I'm going to replace t by w, right? Sine of xw plus y dy, and I'll leave y and x alone. Right, and so this is obviously related to our function u, and in particular, our function u of xt is equal to f, but we're going to replace, remember we replaced w, this was a t, so w should be t, and then we're replacing s by t squared, right? And so, well, I'm going to view this as, right, w as a function of t, and I'm also going to view s as a function of t, right? Where w of t is t, and s of t is t squared. And using this perspective, I can write my function u in terms of this other function f, right? Right, and so now what we're going to do is view my function u of xt as this function f, but w is going to be a function of t, and s is another function of t, in exactly this way up here, right? And so, well, then if I take the derivative with respect to t of u, this is equal to the derivative with respect to t of this expression here involving my function f. But now we're in exactly the sort of situation where you learn to use the multivariable chain rule, right? We can use exactly that. Right. And so let's carry this out. So remember, what is the multivariable chain rule? Well, this says that this is equal to on the derivative with respect to t of this expression involving f, where some of the components are themselves functions of your variable of differentiation. Well, this is going to be equal to derivative of f with respect to x times dx dt plus derivative of f with respect to w times dw dt, and then finally plus the third term, which is derivative of f with respect to s times derivative of s with respect to t. Okay. Okay, so you may wonder, like up here, why didn't we just let w equal, why didn't we just put, like, what's the point of this extra variable w? Well, the main issue is if we just left wt here equal to t here and didn't introduce this other variable, well, we would have kind of a confusing formula over here, which would involve df dt. But on the left-hand side, we had a df dt, and these things are not the same, right? So you would be tempted to cancel them out, which you can't do, right? Because, and so this is related to some technicalities about like, what does the multivariable chain rule really mean, and so on. So this is kind of the reason why we introduced this other variable to avoid confusion at this point. Okay, and well, now the good news is that, well, there are a lot of terms here, but these terms that I'm underlining in blue are relatively easy to simplify, right? So we'll note that x is independent of t, right? So this is just 0, right? On the other hand, well, I know that w is just equal to t, so derivative of t with respect to t is 1, right? On the other hand, we saw that s is equal to t squared, and so derivative of s with respect to t is 2t. Okay, so this is 2t. And so we have this formula simplifying. So this tells us that derivative with respect to t of u is equal to derivative of f with respect to w plus 2t times derivative of f with respect to s. And this is only when evaluated when w is equal to t and when s is equal to t squared. And so now to actually find the derivative, we're just going to calculate these two things separately. using the variables w and s, and then we'll plug in t for w and t squared for s, and then plug it into this formula, and we'll be done. Right. So first, let's find df dw. Right. Well, this is derivative with respect to the variable w of the function f, which was given by integral from 0 to s sine of xw plus y dy. And so now our variable that we're differentiating with respect to is w. And so we're just going to use the same idea we saw in case one, right, where I can bring this derivative into the integral, right, because there's no w up here on the bounds, right? So this is equal to integral from 0 to s of d dw of the integrand, right? And so using the chain rule as we did before, this is integral from 0 to s of x times cosine xw plus y dy, right? And so we're going to plug this into our previous formula now with w equal to t, right? And s is equal to t squared, right? And so setting s equals t squared and w equals t, this is integral from 0 to t squared of x times cosine xt plus y dy. Right? And so now we've calculated the value of the first term. Right? And so now we just need to calculate the value of df ds as well, and then we add these together in this way. Right. Right, so now let's look at df dw, or sorry, ds, right? Well, now this is the derivative with respect to s of our function. Well, now we're actually in a position to use the fundamental theorem of calculus, right? And so, right, because now we're differentiating with respect to s, and s is in the top bound for the integral and doesn't show up inside. And so now we can actually use the fundamental theorem. We couldn't use it up here earlier, as I mentioned, but since we've kind of relabeled things in this way, and now we're differentiating only with respect to the variable that's in the domain of integration, we can use fundamental theorem of calculus. And so this is equal to sine of xw plus s. Right? In particular, fundamental theorem of calculus says that this derivative is exactly equal to the function that's inside the integral with y replaced by s, right? Which is what I have here. Okay, and now again, setting w equal to t and s equal to t squared, this gives me sine of xt plus t squared. Okay. And so this is what df ds is equal to evaluated at these particular points. And so now we're basically done. So let me just plug them in up here. Okay. And so finally, putting everything together, derivative with respect to t of our function u is given by, well, the first term we had here was integral from 0 to t squared x cosine xt plus y dy. And then the second term was 2t times derivative of f with respect to s, right? So that's going to be 2t times what we just got in the previous calculation. So 2t sine of xt plus t squared. And so this is much more complicated than the first case. And so unfortunately, you have to kind of do this calculation every time you have a function of this form that you're trying to find the derivative of. Right, and so just to quickly review what we did here, and then we'll be done. So we were in the case where we had our function u, which was defined as a function of t and some other variables in terms of this integral. And we wanted to differentiate this with respect to t, but the problem was that both the bounds for the integral and the function inside the integral both depended on t. So how do you do this derivative? Fundamental theorem of calculus doesn't apply here, and you also can't just bring the derivative inside the integral because, well, this thing is the domain depends on t too. So how do you deal with that, right? And so the idea is to every place that the variable you're differentiating with respect to shows up, introduce a new parameter, right? So introduce a new variable, say s and w, and view those parameters as functions of t. right? And so then you can write your u in terms of this function f as we did, and then you can use the multivariable chain rule and right as we did here, and then calculate each term separately, which is going to be easier, and then plug everything in, and you'll be done. Okay. So I'll have at least one problem on your first homework assignment where that will give you an opportunity to practice this. Again, I don't know if it's common for people to see this in a multivariable calculus class, but we're going to be using these types of calculations a lot later in the semester, so I just wanted to review them now. Okay, so I guess that's it for now.